So today I thought we would do two things. One, talk about the make command, which you should have now. So if you type mk at the prompt, you should get a complaint that you didn't give it a file name. That's great. If you want to know a little bit about how it works, you type mk-h. It'll dump out a whole bunch of help information that you can read through at your leisure. The other thing I thought we might do is spend a little bit of time looking at the different mul instructions. Seems like a good way to do both. Now, to look at the result of the mul instructions, it's helpful if we can look at the content of a register. There's a bunch of ways to do that, but what we're going to do is we're going to use a little piece of code to do that and print out a 64-bit value in hexadecimal. And that piece of code is in hex.asm. So we're going to take a look at it with the Nano editor. And here it is. This is commented. I don't expect you to necessarily understand everything in here. In fact, I don't expect you to understand everything in here. I just don't. That's okay. We're going to cover all the things that are in here. A lot of this is stuff we haven't gotten to yet. But there are comments in here, and you can read through it if you're interested. This exports a single function called hex that is now available outside of this module. And up at the top, you'll see this. That is the marker that the little make tool looks for. It looks for that in the first line, and then if it finds it, everything after that it tries to interpret. The semicolon in front of it, not important. The space in front of it, not important. Doesn't care, right? That semicolon is just there to keep this from confusing the assembler. Now, the rest of that line, the $make_as, that says, hey, build me using the standard assembly stuff. And we'll see what that is. We don't have the link line that we would often have because we don't want to link this file. This file can't be linked, right? So, you know, when you compile some C code, you compile all your little modules to .os, and then you link them all together into a program or a library. Well, to link this into a program, we'd need an underscore start or a main, and there's none of that in here. All we do is provide the hex function. So we'll need to link it with something else that provides that. So we don't want to link here. We want to link in the other thing that we build that has a main or an underscore start. So let's hop out of this, and let's see what happens when we do make and hex.asm. Well, make prints out the line that it uses to do its work right here. And so you can see it called NASM. NASM is the net-wide assembler that we'll be using to assemble our code. It tells it the format it wants the result to be in this case, a 64-bit ELF file. It tells it what the input file is, hex.asm, and it tells it what the output should be, hex.o. Now, it created a .o file. And if we take a look at that, it's just a standard elf.o file. In fact, it's not really any different from one you would create if you were writing programs in C or some other language. And it can, in fact, be linked with those, and you can use a little hex function from a piece of C code. It just works. Really, trust me. So, just in case you don't trust me, I created, try hex.c. There we go. So this is C code. And we'll ignore the top line for right now, but you can see that we go ahead and include int types.h because we want to be good citizens and use the types that actually specify their width. And then down here on this line, we have a prototype for a function. We have a prototype for our hex function. It's going to take a 64-bit unsigned value. It's going to print it out for us, and it's going to return to us an int, because that's what write returns, and it uses the kernel's write function. In general, you should not use int. I'd be happy making this void, but I want to be really, really systematic about it. Down here is a main function. Oh, we have a main function, so now we could conceivably link it. I'm going to try to always write the main function with all three of the arguments, just to emphasize that they're all three there. So argc is our number of command line arguments, argv is the command line arguments, and envp is the environment. And some of you may be wondering, why don't we know what the size of envp is, right? We know argc is the size of argv. What's the size of envp? It turns out you don't need this guy right here at all. You don't need it. You can throw him away and be perfectly happy, because these two arrays, argv and envp, are both null terminated, which means that there are a series of pointers, right? This is an array of pointers, in this case to char stars. It was pointers to characters. And once you've hit the end of the array, the last entry in the array is a null pointer. So you can walk through the array just looking for that null pointer and know how many entries there are. In fact, that's how the C runtime goes from what the kernel provides, which is just argv and envp, to what the C main function needs, which is also argc. It computes that for you and passes that along. So down in here in the body, we call hex with the value 1. We call it with the value of 4 Fs and 4 zeros. We call it with 1,000, 2,000, 3,000, 4,000. Then we call it with 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and 0. Right? We do this in hex so we can see if the result looks like what we expect. Now, how do we build this? Well, I made a build line for it up at the top because I'm weird that way. So there's our little comment to indicate to the C compiler it should ignore this line. And there's our little make : token that's going to tell our make system to go and do something with this. And you may be interested in this. So can make call itself? Yeah, it can call itself recursively. And so the first thing we want to do is go and be sure that we've done make on hex.asm. Because if we haven't, we need to, right? It's a dependency for this file. So we're going to go and recursively run make on this, and that's going to work. This little ampersand, double ampersand you see, that's a bash or a Z or a bunch of other shell ism that says if the previous command succeeded, go ahead and do the next one. So if my make of hex.asm fails, I'll stop right here. But if it succeeds, I go ahead and what do I do next? I do gcc-o and this. This is the base file name without any stuff on the end. So since we're in tryhex.c, this converts to just tryhex. And what's this? Well, this is the file we're in now, which is tryhex.c. And then we have to, of course, link with our hex.o, so we include it at the end. Right? This is how you would, I'm sure you've compiled C code. I hope you've compiled C code. This is how you would compile a program in C that consists of multiple pieces, right? You compile the thing with the main function, you add all the .os for the other stuff you need, and then you give it a name for the output, and there we go. So that's going to, we hope, build this for us. And let's try it. So we'll try make try hex.c, and this time we get more than one line of output. We get this line right here, which, if you remember, right, it says go and make hex.asm and then do this. Okay, well, it has to go and make hex.asm, so it also prints out the line that builds hex.o here from hex.asm. And then it can go back and do this GCC. It does all of that, and we wind up with try hex. And let's try hex. And we get just what we should get. We get 16-bit hexadecimal output. The first thing we tried was just 1, and it prints out that. 15 zeros followed by a 1. The next thing we tried was 4 Fs and 4 zeros. And so there's 8 zeros, 4 Fs, and 4 zeros. Then we tried 1,000, 2,000, 3,000, 4,000. And finally we tried 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 0. And there they are. It works. And we were able to call it from C. And the reason we're able to call it from C is something we'll talk about in a future class, which is because the code I wrote in hex.asm follows the calling convention that the rest of Linux expects you to follow. So it knew where to put values and what registers to put them and what to put on the stack. And my little program behaved as a good citizen. It didn't mess up anything it shouldn't mess up, etc. And it all just works. So integrating C and assembly, or really most any language in assembly, is actually fairly straightforward. You'll have a calling convention that you'll need to observe, and once you've done that, you should be in good shape. So over the course of the semester, we'll call C from inside assembly. We'll call assembly from inside C. We might do other crazy things. You don't know. But that works just fine. So I did promise you something with ASM. With MUL. There we go. I'm getting the wrong acronym in my brain because I haven't had enough coffee. I did promise you stuff with MUL, and so it turns out I have made some MUL files. So let's go ahead and take a look at mul1.asm. So here it is. Up at the top, you'll see what should be by now familiar, a little comment line so the assembler doesn't get confused. And then here's our little mk : token. And then after that, we need hex.asm, so we make it. It's a dependency. And then if that works, we go ahead and tell it this. Now, what is all that? Well, this says assemble this file, and if that works, link it. So we haven't seen that before. So this guy right here expands to the appropriate linker command. And so we're going to link our file, and we have to put hex.o on the end because we're also going to include hex.o. By default, this will include the .o version of this file, but it will also now include hex.o. And we'll see that when we run it. So in here I have global start, and I have extern hex. Extern hex? Yes. Just like in C, when you want to use something that's external, you need to say extern. You may not have necessarily had to do that because of the way we have you write C code, but you can. That says that this is defined somewhere else, and you should expect to go find it. And so the job of the linker will now be see if I can locate something that provides hex. And it will in fact find something that provides hex because we gave the linker hex.o, and hex.o provides hex. So it'll all work out. It'll find it. This right here is a moderately new thing. It has to do with warnings that the GCC compiler and that the linker will all generate if you have writable stack. And so you need to explicitly indicate that you don't have, executable stack, that you don't have executable stack. We don't want executable stack in your program for security reasons. And so this is a marker to indicate that we don't have executable stack. We then have a text section. That's where your executable code is going to go. And here's our executable code. Scroll down just a bit so we see it all. So up here at the top, we have our _start, which starts it off. And then we do some stuff. In this case, we're going to put a bunch of Fs, 16 Fs. Right? So we're going to set RDX to all ones. And we're going to set RAX to 64. And remember, RDX and RAX are the ones that are affected by the mul instruction, which just has one argument. And so we set RBX to 2, and then we do mul RBX. Now what's going to happen here? Well, when we do this, we're going to multiply RBX, which is 2, by RAX, which holds 64. 64 in hex is 40. Right? 4 times 16 is 64. It's 40. So a successful multiplication should give us back 128. Or 8 16s, which we'd write as 80. So we expect to see 80 when we print out the hex. What about this RDX value? Well, will it just get shifted over? What will happen to it? We'll find out. So we do the multiply here. And then down here, we're going to print out RDX and then RAX. Well, RAX is modified by our little hex function. So we save a copy on the stack. Just push RAX onto the stack. that doesn't change what's in RAX right now. It still holds its value. We've just put an extra copy of it on the stack for later. We put RDX into RDI. RDI is where our little hex function expects to find its first and only argument. So we put RDX into RDI. We then call our little hex function, which will print it out. So it's going to print out RDX's value. Then we do a pop RDI. Well, what's happening here? Well, the value that we pushed on the stack was the value in RAX. And so now when we pop that value into RDI, it's just as if we'd put the original value of RAX into RDI, right? We can't do that right here because this call changed the value of RAX, which is all perfectly legal. And so we have to be careful. And so we put what's in the stack, top of the stack, back in. This is why you have to have some stack discipline. We don't want hex to mess up our stack, and we don't want it to mess up certain other registers. This is important stuff that we'll talk about when we talk about calling conventions. So now the RAX value for my multiply is in RDI, and we call hex and print it out. So hex is we're going to use hex to print out RDX and then RAX after the multiply happens. And then we just exit down here. So remember, we're taking all ones and 64, which is hex 40, and multiplying that by 2. And so let's see what happens. So we're going to do a make on mul1.asm, and you can see what happens. It does the make on hex.asm, which leads to the line below it where it builds hex.o. It does a NASM on mul1.asm, and outputs that as mul1.o. So now I have a couple .o files. And then over here it links, LD is the linker. It links with the output being mul1, the two files mul1.o and hex.o. And then we should be in good shape. So let's do a file on mul1. And it says, hey, this is an ELF 64-bit executable. So let's go ahead and run it. Remember, we're doing 64 times 2. We should be 128. In other words, we should see 80 in hexadecimal. And we run it, and we first see RDX, which started out as all ones, but now it's all zeros. Its value got completely thrown away. And we see that, sure enough, hex 40 times 2 is hex 80, just like we expected it to be. Great. So this tells me that when I multiply RAX by some value, I always wipe out or overwrite whatever's in RDX, and have to keep that in mind. Here's a second mul. Same stuff at the start, nothing to see there. And we see that we are doing very similar stuff. We load RDX with a bunch of ones. We load RAX with 64, and then we're going to multiply it by 2. But now we're using the signed multiply, imul, and then we'll print everything out the same as we did before. So let's hop out. Let's make mul2.asm, and let's run it. And we get the same thing. It wipes out the value in RDX, and sure enough, positive hex 40 times 2 is positive hex 80. Nothing to see or write home about there. So let's go ahead and take a look at mul3.asm. Again, pretty much the same stuff. Same stuff at the start. Except now we do the same loading here. Now we're using the 2-argument version of imul. So what I'm saying here is take RAX and multiply it by 2. Do we need RBX at all? Well, just to see, let's go up here and change it to 7. Just to see, right? So then I would have 64 times 7, which is certainly different from 64 times 2. So let's see if RBX is used or not, and let's see if RDX is used. Let's go ahead and do make mul3.asm, and then we'll run it. And a couple things to notice. RDX was not touched by this. And RBX clearly wasn't used because all we did was multiply hex 40 by 2. So that worked beautifully, no problem there. Let's do another change to it. Instead of doing imul RAX and 2, let's try imul and RAX and RBX. Now we shouldn't get 64 times 2. We should get 64 times 7. So what is that in hex? Do you know? Can you figure it out? 64 is 4 16s. If I multiply that by 7, I get 7 times 4 or 28 16s. That's going to be quite a few. That's going to overflow, right? So I have more than 16 16s. So how many more? Well, 28 minus 16 is 12. What is 12? 12 is C. Okay, let's take a look and see what we get. Sure enough, we get 1 because we have 16 16s, and C because we have 12 remaining 16s. So yeah, that works. You can multiply by a register in that way. What about the 3-argument version? So now I have the same exact stuff, but now what I want to do is take RBX, multiply it by 2, and put it in RAX. Okay, RBX holds 2, so 2 times 2 is 4. Let's see if that works. And RAX's value of 64 shouldn't matter. It should just be discarded. And it is. So RDX is not touched at all, and RAX gets 2 times 2, which is 4, and we're done. Now, you can play with these. We're using imul, so we're using signed values. I didn't do anything here, it was negative, but you can try that out. All of these have been uploaded in a little package on the extras site of the course content, and you can have a look at that. And there's a few more tricks I want to show you here. So I've already showed you that you can call make from within the make line. That seems fine. What about this? So this is a file that only contains a make line. Really, the semicolon is overkill. I don't know why I put it in there. But it has this little make token here, and then it says make mul1 and mul2 and mul3 and mul4 and make tryhex.c. This is my make all. And it does just what it says on the tin. It will build everything. The astute among you may have noticed, hey, it's building hex.o 1, 2, 3, 4, 5 times. Yeah, it is. It is not checking timestamps on anything. It's not it's not make. I'm not reconstructing make here. It's a simple little tool to do this kind of build stuff. And it turns out it's really useful. In addition, sometimes I like to have things clean, and so I made a make clean. So right now my directory has a bunch of stuff in it. I can say make clean, and now I only have a tiny little number of files in here. And this is what you'll get if you download the little TGZ file that's up on the iLearn. So that's a little bit about how make works. That's a little bit about multiply. And that's some little code for you to play around with and see how things work.